It's nice to be back in ICTS. So what I plan to do today is to give a general introduction to string field theory and then show how it can be used to develop string perturbation theory. Okay. But I'll begin by describing the problems with standard worldsheet formulation of superstring perturbation theory. And so for this, let's start by writing down the expression for the string theory S matrix that we are familiar with. Okay. It's normally written as an integral. Okay, first of all, there is a sum over genus weighted by the string coupling to the power 2g. Okay. And then it's written as an integral over the moduli space of Riemann surfaces, okay, which I denote by dm, and some integrand, which I'll not write down now because we will develop this systematically as we go along. Okay. So this is correlation function of vertex operators. And it's known that this expression that we have for string S matrix elements is free from ultraviolet divergence. Okay. But at the same time, it suffers IR divergence as in QFT. Okay, and in fact, we will see that it has other kinds of divergences which can also be classified in a broad IR category. Okay. And this fact makes it almost a useless formula if we take it too seriously. Okay, and I'll explain what I mean by this. Okay, and we will see that in almost all physical cases, this formula is strictly divergent. Okay, it gives infinite answer for physical quantities. So the question is how to cure this, and this will be the main goal of this talk. And to understand this, we will start by reviewing the IR divergence QFT. So IR divergence in QFT. Okay, so let's start from there. So in quantum field theory, a Feynman amplitude typically has the following structures. You have the integration over the loop momentum. And then you have a product of propagators. And possibly multiplied by some polynomial in K, in the loop momentum. This is a polynomial. So these could come either from the vortices or from the numerator of the propagators and so on. And I'll assume throughout that we are using Feynman type gauge so that the poles in the propagator are always of this kind. Okay, there are no other kinds of poles that we'd encounter in either Coulomb gauge or axial gauge, for example. So from this perspective, the ultraviolet divergences come from when the loop momenta become large, one or more loop momenta become large. As we said, those divergences are not present in string theory. But the infrared divergences these are associated with one or more factors of ki square plus mi square becoming 0. Okay, this will be my general definition of what I mean by infrared divergence, quantum field theory and string theory. Now, when we try to compare this with the corresponding string theory result, okay, in string theory expression over here, we don't see explicitly these momentum space integrals. Okay. So, in order to translate this to a language where you can compare with string theory answers, okay, we have to use what is called the Schuringer parameter representation. So here we replace each of these factors by integral 0 to infinity okay. For each propagator we introduce a, let's call it SI, introduce a parameter SI which is the Schuringer parameter and replace it by this integral. Then we substitute here and then do Li mu integrals, which now is reasonably straightforward to do because what we have here is a Gaussian. Okay, each of these is replaced by an exponential. You can express each Ki as a linear combination of the loop momenta and the external momenta. And so you have a Gaussian factor, and this is of course just a polynomial in L. Okay, so you can easily carry out the integration over the loop momenta now. Okay, and then express the final answer as integral product I dsi. Okay, each, let me write it as each of them run from 0 to infinity and some function of s. Okay. And in this language, in a quantum field theory, UV divergence come from Si goes to 0, okay, and IR divergence come from Si goes to infinity. Okay. And as I have already said that these are not present in string theory, these are absent in string theory. These however are present in string theory. Okay. And the way to see this, okay, is to make an identification, okay, which you can do by comparing the integrands and appropriate limits. Okay, that these parameters Si, so QFT, if you want to compare QFT with string theory, then these parameters Si that you see here, which are the Schuringer parameters, these become roughly the moduli parameters of the Riemann surface. Okay. And the Si goes to infinity limit, Si goes to infinity limit corresponds to, on this side, degenerate Riemann surface. So what are degenerate Riemann surface? Okay, degenerate Riemann surface is when one or more of the cycles of the Riemann surface get pinched, okay, to a very narrow cycle. Okay, so for example, this is the example of a degenerate Riemann surface. So you can have some Riemann surface, okay, with some vortex operators inserted possibly. So this is a genus 4 Riemann surface, but when this cycle becomes small, okay, that's the degeneration limit, and in that limit we can make an identification that the size of the circle is goes like e to the minus s. Okay. There is another kind of degeneration, okay, where the Riemann surface doesn't split up, but it still develops a narrow handle. So let me try to draw this here. Okay, so this is what is called separating type degeneration. Okay, it just splits up into two parts. Here, this is non-separating type. You can nevertheless pinch this, and this is a singular limit. And if you try to compare this with the corresponding Feynman diagrams in a quantum field theory, okay, these degenerations correspond to So if you take a Feynman diagram of the following form, okay, this is an arbitrary blob. Okay, take a Feynman diagram of this kind, and suppose this Schuringer parameter goes to infinity. Okay, these kinds of degenerations, these kinds of Feynman diagrams, okay, in the S goes to the infinity limit, corresponds to the degeneration that you see on the left. And you can also consider degenerations of this kind, where the propagator whose S is going to infinity is such that while cutting it, it doesn't divide into two surfaces, but just one remains a single connected surface. This corresponds to degenerations of the kind that you see on the right. Okay, and you can roughly see the correspondence between these diagrams over here and that diagram over there. That's right, yeah.
And that was for both of these cases.
Exactly, that's right, yeah. Okay, now let's try to see where the divergences can come from. So we again go back to quantum field theory, because as I have already said, infrared divergences in string theory are similar to those which arise in quantum field theories. Okay. So essentially we look at this formula, okay, and see where can we possibly get divergent result from the Si goes to infinity limit, right? Because those are the limits that corresponds to degeneration on the Riemann surface language. So we have ki square, let me just write k square plus m square inverse
all the infrared divergences in QFT only of these two kinds? I mean, some things like even collinear divergences.
Yeah, that's also when one or more momentum are becoming on shell, right? So when you convert to Schuringer parameter representation.
But not only on shell, but parallel.
That's right. So it's becoming, so that means that one massless particle is dividing into two massless particles, right? But the divergence comes when all of them are becoming on shell, right? So when you write in the Schuringer parameter representation, a collinear divergence of this kind will correspond to the S parameter, correspond to this, and this going to infinity.
But I was trying to see when they fall into these two classes.
Yeah, so there will be more lines like this, if that's what you mean, right? So instead of having one line, so this is a loop, for example, collinear divergence, okay, we can have things like this. So this is a loop, and the S parameters for these are becoming infinite, right? So it's a combination of these, that there will be, instead of, these are the basic ones, right? But it can happen that more than one of these lines are going on shell, right? That's what will happen for the collinear divergence. Yes. Yes, so field theory, that's what I'm going to discuss now. Okay, the field theory does have those divergences. We just don't see it. We'll see why. Okay, that's exactly what I'm going to discuss now. Okay, so let's look at this object over here. Okay, now here you can see that where can the divergence come from here? Okay, so first we can consider the case when k square plus m square is negative. Okay, k square plus m square, let me remind you, is minus k0 square plus k vector square plus m square. Okay, when this is negative, of course the left hand side is perfectly finite, okay, but this side is infinite. LHS is finite, RHS is infinite. Okay, so in quantum field theory, remedy for this, in QFT, we can work with left hand side. We don't just use Schuringer parameter representation, right? We can choose to work with the left hand side. But in string theory, it is not possible. Okay, at least not in the naive string worldsheet description, because there is no analog of the left hand side. Okay, there you get the result in terms of the Schuringer parameter representation. Okay. And this divergence will arise even at the tree level, right? In quantum field theory, if you consider tree level S channel diagram like this, whenever the center of mass energy is above the threshold, okay, this line will have k square plus m square negative, okay, and you will get divergence of this kind. So if you use Schuringer parameter representation in quantum field theory, you will get exactly these divergences. These are the ones that Subrata was referring to. This comes, for example, when you calculate the Venezian amplitude. When two operators come close, okay, that's a degeneration of this kind. Okay, that's in the language of Riemann surface, two operators coming close is a degeneration of the kind where you have two vertex operators here, two vertex operators here, and this cycle is degenerating. Okay. And there you see the divergence, okay, in the Venezian amplitude, okay, and that's of this kind. Again, in string theory, we don't know how to use Feynman parameters, right? In string theory, we only know how to use Schuringer parameters. In Feynman parameter representation, yes, I mean, you can use contour integrals, because in Feynman parameter representation, you still have the momentum integrals, right? And you have to be careful about defining the momentum integrals appropriately and define the contour in the Feynman parameter integration space appropriately.
So the Feynman parameters we can also do the momentum.
Yes, exactly. Yeah, here also there is a remedy that I'll discuss. In the Schuringer parameter representation also this can be repaired, right? And that's what I'm going to discuss now. So this solution doesn't exist in string theory, but there is a second solution in quantum field theory. Well, Feynman parameter will be the third solution, but we don't want to use Feynman parameter. Okay, I should say that because of these divergences, this type 1 divergence that I mentioned, okay, this basically makes almost any amplitude that we write down in string theory using the worldsheet representation divergent. Okay, if you just put it on a computer and try to evaluate it, you'll get infinite answer. Okay? And generally one can show that whenever the external energy, total incoming energy, is above the threshold of production of any state, any intermediate state, you have this divergence. Okay? And that is almost always the case, right? Because you can always produce the initial state as a final state. Okay, so you're always above the threshold of production of some final state particle, and then you encounter this divergence. Okay? And this is in fact good, because if you didn't have this divergence, okay, if you see the quantum field theory representation after you have integrated the momentum, okay, the integrand is perfectly real. Okay, so you'll get a real answer. So if the answer is not divergent, then the answer is real. Okay? And that, of course, you know is manifestly inconsistent with unitarity. Okay? So you better get a divergent answer so that you know that they are doing something wrong. So the second remedy in quantum field theory, I epsilon prescription, is to change this equation and write it in the following way. And at the end, you have to take epsilon goes to 0. Yeah, this is S has to be integral on the imaginary axis. That will not help, because then if you to the left of the imaginary axis, well, then there will be other singularity. Then when k square plus m square is positive, you will get singularity, right? You will get problem in the T channel. So you really have to do it like this. Okay? This we can show is the remnant of weak rotation. If we in quantum field theory, if you define the amplitudes by weak rotation, right, this is the prescription that you end up with in the Schuringer parameter representation. Okay. So this can be generalized to string theory. Okay, and in fact this was done by Berera in the mid 90s and then reformulated by Witten more recently. Okay. So this can be done in string theory, can be done in string theory. Okay. But the price you pay is that you have to define integration over M, the moduli, in complexified moduli space. No, that's not what he said actually. That was Docker and Fong, they use imaginary Mandelstam variable and continued. Berera actually described the procedure for real Mandelstam variables. That basically you need this continuation in the moduli space. Yeah, so this basically is how in tree level, for example, what it means is that if you think of the integral over z and z bar, normally you think of integral d to z as integral over two-dimensional plane, right? But what you have to do is you have to think of z and z bar as independent variables, okay? Independent complex variables, okay, and define a contour in that two complex dimensional space, and that's what you integrate over. See, because you see that normally you will think of z and z bar in this language as e to the minus s plus minus I theta. Okay, and z and z bar are complex conjugates, so you'll think of s and theta as real variables, right? But this integral is done not over real s, but over imaginary s. Right? In fact, you can take this contour from 0 to some real number and turn the thing towards imaginary axis. It gives the same result. Okay? But you have to do something like this, and this in this language means that z and z bar has to be thought of as independent complex variables. Right? You define a contour appropriately induced by this in that two complex dimensional space, and that's the contour along which you have to integrate.
So half-dimensional.
Yes, it's a half-dimensional plane, so that you are not changing the dimension of the space on which you are integrating. Right? But it's not the two-dimensional real z bar variables, and for which, as Subrat mentioned, you always get divergent answers, right? And because of the short distance singularities, and that short distance singularity is precisely this, right? It's this generation which causes that divergence.
How do you choose the particular half-dimensional space? It is determined by demanding that this integral converges.
No, near the boundary, you can introduce an analog of the parameter s, and this is the way you define. Right, that this has to be done only near the boundary, right? So what you can do is that you can integrate over the real moduli space almost till the boundary, right? In the near the boundary, you introduce this parameters s and theta by analog of this, or any degeneration has the analog of s and theta parameters, and then that s parameter, instead of running to infinity, you turn it towards I infinity.
There should be a certain sense in which you have to do it smoothly.
Well, you don't have to do it smoothly. You can do it like this. When it has to be continuous, right? But the s integral in the complex s plane, you can just do it like this, right? And the result, because of the fact that it's an analytic function of z and z bar independently, right? It doesn't matter if you deform the contour, right? I mean, this is the same as integrating along this contour. Yes, you have to make sure that there are no singularities, right? And that's what this procedure does. That if you turn the contour in the complex plane near the boundary, right, then you can show that there are no other poles. I mean, you make this result finite by this procedure. Yes, yeah.
Is it, here it still involves a cancellation of some very large quantities, because you could
Yes.
So you get very large answers. And then you start circling around the boundary.
That's right, yes.
So in the end, it's still not something one can put in the computer. Because it still involves one very large quantity having a delicate cancellation with other large quantity.
Yes, but you can still put it in a computer as long as the external energies are finite.
That's also because you cut off the modularized space very close to the.
Yes, so the point is, so the things which will give divergent are the ones below threshold. Those are the ones which have negative k square plus m square, right? But that's a finite number of states. Right? So only a finite number of states will give large contribution. Right? The sum over infinite number of states, right, will be convergent because those are below threshold. Right? So when you go close to the boundary, what it is true that it's not efficient, right? Because you go very close to the boundary, you get a lot of contribution from the ones below threshold, but it's still a finite contribution.
But I didn't understand why. I didn't understand why do you go very close?
We don't have to. You can turn it, yeah. But if you turn it too early, right, then you don't suppress contribution from heavy states. You see, the advantage of having S running along the real axis is that for larger and larger M, this is suppressed, right? So you want to have that feature because otherwise you will get a lot of contribution from the heavy states. Right? So you have to go somewhat towards the positive side and then turn, and you can adjust that according to your need. And the point is, for any finite value, as long as you go along up to a finite value and then turn a contour, yeah, you will get a convergent answer because the sum over the infinite number of states always converges because those are above the threshold. Exactly. Yeah. Yeah. You can just go some distance and turn because the result is independent of how you turn it. Right? It's because it's a two-dimensional contour integral, right? It's a contour integral in a two complex variable, for example. And it's an analytic function of z and z bar. Right? So you can easily deform this contour to this contour without encountering any singularity.
So let us say I have some vertex operators.
Yes.
Some external states which are colliding.
Yes.
Which totally the total energies let's say added to some
Exactly.
number times string scale.
Yeah.
String mass. And then so maybe twice that mass I can turn.
Yes, you can do twice that mass and turn. Right? So what will happen is that, so you can, yeah, so you go twice the mass and turn. So what will happen is that the ones which are below the threshold, right, those contributions will become larger and larger as you go closer and closer to positive axis, because you can see that this is growing, right, for k square plus m square is negative. Okay? But for all the heavy states which are above the threshold, right, this is negative, so those will be suppressed. Right? So there is a choice you have to make, that how far you want to go, right? You want to suppress the contribution from heavy states, but you don't want the lighter states to become too dominant, because then that will be cancelled by some oscillatory contribution over this part of the integral. Right? So,
of course, the final answer would be correct.
yes, exactly.
How efficient it is.
Exactly. So where to cut it off? Right? That depends on your computer skill. That, I mean, you have to decide on where exactly you want to turn the contour. Is this clear?
IL processing, you write time ordered correlation.
Yes, it always will give time ordered correlation.
What is analog of time ordering?
Out of time ordered correlation, yeah, I have no idea. Meaning, the point is, the Euclidean correlation functions can be defined using string field theory, but how to extract this out of time order correlation function, I don't know from there. Okay, so now we come to the other kinds of divergence, which are genuine ones. In string field theory it is. The string field theory provides that parameterization. That's exactly one of the goals of string field theory, to provide the parameterization of the complex variables, because there you really see this S and theta coming from the propagators, right? And there you can just turn S all the way from 0 to infinity, 0 to I infinity. Yeah, otherwise if you want to do it ad hoc, then you have to make a parameterization where you cut off, put the S integral up to certain value and turn it, right? But that becomes completely natural once you use the language of string field theory. Yes. The problem is the light cone diagram, at least in superstring field theory, is that there are various contact terms and that those are never been understood properly. Right? I think if one could understand the contact terms properly, then that automatically has these lengths, right? So you could imagine that turning those lengths in the along the imaginary direction. Yeah, so for bosonic string theory, I suspect that this can be done. Right? And for bosonic string theory, light cone diagrams will provide a parameter of this S, and you can turn it. Okay, now I should just say here that this procedure, okay, not only makes things finite, but it also generates imaginary part, because now the S integral is running over I infinity, to, from 0 to I infinity. So this does give also imaginary part of the amplitude, so that danger is not there. Okay. Nevertheless, to prove unitarity is hard here. Proof of unitarity is hard directly. Okay, and so far it has been proved only by showing its equivalence to string field theory and then showing that the string field theory gives unitary amplitude. Yes.
You said you want to be talking about payment parameters, but there's something you can say about payment parameters. What is the corresponding story?
I think once you write it in the language of string field theory, then you can do whatever you can do in quantum field theory, in string field theory, and there you can use Feynman parameters. Right? So when I write down the result in terms of string field theory, then there will be regular 1 over k square plus m square, right? And there you can certainly use Feynman parameters. For example, studying analyticity of the amplitude, the Feynman parameters may be a better suited description. So that you can certainly do. Yeah.
What would be the proof of unitarity hard directly? What exactly?
For example, cutting rules. The fact that the imaginary part of the amplitude that you get this way is given by the sum over cuts. Right? That has not been established in the, with this Schuringer parameter representation. Yes, but again, when you try to prove equivalence to light cone gauge, there are various contact terms. Right? Roker and Fong's analysis, which they did in the mid-90s, right? Yeah, they basically didn't take into account all the subtleties that the superstring perturbation theory has, right? So maybe one can try to go back to their analysis and try to incorporate whatever has been learned in recent years in their language, right? And that may be a possible proof of unitarity.
So what is the physical origin of this contact?
Basically, it's from the picture changing operator, because what happened, the light cone gauge string field theory puts the picture changing operators at very specific places and they collide, right? And that's what gives rise to these contact terms. And it has not been understood how to distribute the picture changing operators appropriately in the light cone gauge.
Is that the one lead that you think?
Yes, I think that is the only subtlety. That is, the contact terms basically come from the picture changing operators. Okay? And the freedom of moving picture changing operators, which we'll discuss, that which exist in covariant formulation, because you have the ghosts. Right? In the light cone gauge, you don't have the ghosts, right? You have already interior the ghosts, and there you cannot just move the picture changing operators arbitrarily. Right? And that's where the difficulty comes. And the place where they are put, they collide as you go towards regeneration. Right? And that's not the correct procedure that one wants to use.
So there is this formalism, pure spinor formalism, there are no picture changes.
Yes. So as long as the pure spinor formalism works, right, there you can try to use, basically you can try to do the calculation directly. Right? But again, how to get the imaginary part, right? The same difficulties will arise even in that case, right? That you have to be able to define the imaginary part appropriately, right? And I suspect that it can be done in the same way. Okay? But again, to show that that particular procedure for giving imaginary part is consistent with unitarity, I think is going to be hard. Right? Because it's hard even in bosonic string theory. That in bosonic string theory, one way to show unitarity is by making contact to the light cone gauge. Right? But in the covariant formulation, directly showing unitarity is hard. And I think that will exist, continue to exist in pure spinor as well. Yeah, that is true. But see, there are two aspects. One is that you have to show the decoupling of the pure gauge states. Right? That's the second part. But the first part is that if you use, when you use the Schuringer parameter representation and define the integral by turning it this way, okay, you have to show that this is consistent with cutting rules. Right? You forget about whether the intermediate states have only physical state sum. At least the fact that the imaginary part is given by the sum of all possible intermediate states. Right? That you have to. That's the first step. Right? Even that has not been done in this formulation directly. Okay, so the second kind of divergence are the genuine infrared divergence. Okay, so let me write down the expression again. Yes.
Can't one show that the imaginary part is not divergent and deform the contour back to the real thing and show that the
because the point is there are many contours, right? Many S parameters integrated at the same time, each being turned in the imaginary axis, yeah. Right? And I think so it's hard to, so it's not even true that the imaginary part is not divergent, right? Because the imaginary part is a sum over the product of amplitudes on the two sides, right? Yeah. Each of these amplitudes themselves can have divergent parts.
Okay, I mean, I'm assuming that, I mean, if you are considering divergences coming from a particular Schuringer parameterized thing, the imaginary part will not have that divergence.
Not that divergence. Yeah.
Okay. The divergence, if we assume that we have taken in somehow.
Yeah. So the point is, so the imaginary part is not divergent, but the imaginary part is coming only because you are integrating from 0 to I infinity, right?
The I epsilon. I mean.
Well, yeah, it's I epsilon, but eventually you are taking epsilon to 0, right? So the fact the imaginary part in this language is coming because the integration is being done over the imaginary axis. Yeah, at the end you will take the epsilon goes to 0 limit.
Even if we took it along the real axis very naively, suppose k square plus n square was always positive, and we just took it along the real axis, you would get 1 over k square plus n square minus I epsilon. And
yeah, if it was positive.
If it was positive.
But if it is negative, yeah, right, then this is ill-defined, right?
Right. So that's why you are deforming the contour.
Exactly.
What I was saying was the imaginary part.
See, imaginary part comes only from those which for which this is negative, because those are the ones below threshold. Right? So for the ones for k which k square plus m square is positive, we could make this and take this along the real axis, right? And those don't contribute to imaginary part.
Those would give you the delta function.
No, because those are all above threshold, right? If k square plus m square is positive, then yeah, they are all above threshold. Exactly. Right? So the problem comes from k square plus m square less than 0, and those are also the ones which are responsible for the imaginary part. Right? Because those are the ones which are forcing you to have the contour in along the imaginary axis. Okay, are there other questions on this? Okay, so let me then describe the second kind of divergence, which is the genuine ones. When k square plus m square is 0, then the left hand side diverges and the right hand side goes to infinity. Okay, so these are what is called genuine infrared divergences in the theory. Okay. And these divergences can arise from many different Feynman diagrams. Okay, I'll describe some simple examples. Okay. So take a Feynman diagram like this. Okay, 4-point scattering, on cell 4-point scattering. This one has 1 over k square plus m square. Okay. But this k that is flowing here is the same as this k over here. Okay. This line is on shell. Okay. So k square plus m square is 0. and this blows up. Okay, this is of course you are familiar with. Okay, these are the self-energy insertions on the external lines. Okay, and in QFT we know what to do with it. In QFT, remedy in QFT is to use LSZ and mass renormalization. Okay, so you basically use the resummed propagator and you don't use external propagator at all. Okay, instead of that you just ignore all diagrams of this kind. Okay, use the appropriate renormalized mass for the external particles and put an appropriate wave function renormalization factor here. The second example is massless tadpole. Okay, just imagine that this is a massless line. This is massless. So you will get a 1 over k squared, okay, but evaluated at k equal to 0, so this is infinite. Okay. And again, we know how to remedy this in quantum field theory. Okay. In QFT, all it means, so in QFT, we need to go to a new vacuum and do perturbation theory over there. So basically the existence of a massless tadpole means that the original classical vacuum that you started with is getting destabilized. It's not a solution to the of the quantum corrected equations of motion anyway. Okay. And hence we have to go to a new vacuum which is actually a solution to the general quantum corrected equations of motion and do your perturbation theory around the new vacuum. Okay. So in QFT, okay, while these divergences do exist, okay, we know how to repair them. Okay. And then there are more general infrared divergences of the kind that appear in loops. Okay. Those appear in 4 or less dimensions. And again, in quantum field theory, we have a very precise understanding of how to remove those divergences. Okay. But unfortunately, we don't have these options in string theory. So in string theory, okay, and there are good reasons for this. First of all, mass is fixed at tree level, is fixed at tree level, requiring BRST invariance of the vortex operator or conformal invariance of the vortex operator. So this is not changeable in perturbation theory, right? If you try to change the mass, you basically destroy BRST invariance of the vortex operator and then you don't know how to deal with such situations. Okay. Similarly, the vacuum is fixed by demanding worldsheet theory to be conformal. Okay, so if you want to shift the vacuum, okay, you destroy this property, the worldsheet theory no longer remain conformal, and hence again you don't know how to deal with such situations. Yes, if you can shift the vacuum keeping the worldsheet theory conformal, right, then of course you are fine, right? But typically what will happen is that when you have tadpoles like this, that you will go to a new configuration, which is not a solution to the classical equations of motion, right? And that means that the worldsheet theory is not super conformal. It's not a solution to the classical equations of motion. It's a solution to the 1-pi effective action, right, which includes quantum corrections. Right? So if it's a solution to 1-pi effective action and not of classical action, that means you are destroying the worldsheet conformal invariance. Right? So the worldsheet perturbation theory that we normally develop, that breaks down in those cases.
So the beta function of the worldsheet sigma model,
yes,
is what we call as the passive.
Exactly. So the beta function of the worldsheet sigma model will no longer be 0 if you go to this new vacuum. Right? So for example, you cannot define BRST operator anymore on the worldsheet.
There's no sense we can talk about like genus corrected.
Well, the string field theory that I'll be describing is the sense in which you can talk about genus corrected thing, but it's not the worldsheet perturbation theory. Right? I mean, you have to reformulate the worldsheet perturbation theory in the new language.
This Massless thing tried to do that.
Yeah, they tried to absorb these genus 1 corrections into a correction to the beta function, but that was never really done very systematically. Beyond one loop, exactly. I mean, I would say string field theory is a systematic way of doing it. I mean, what you'll see is that in string field theory provides a way to cut off the or organize the divergent regions, the boundaries of the moduli space, okay, separately, and that essentially puts an effective UV cutoff on the worldsheet theory, right, and does what Sdse-s is supposed to have done. Right, the string field theory is a systematic way to cut off the ultraviolet divergence, because the main problem is that if you try to do Sdse-s, right, you have to have some notion of an ultraviolet cutoff on the worldsheet theory, right, and then you combine the contribution from small genus contribution from the with the worldsheet divergences, and there is no natural way to compare those cutoffs, right. There is a cutoff from the small handle, right, and there is a cutoff on the short distance on the worldsheet. Then there is no natural way to combine them, right. String field theory gives a way, natural way to combine them. But of course, there are ambiguities in how to do this, right? And the task is to show that the final results do not depend on these ambiguities. So basically our task, okay, or our approach is to use superstring field theory to solve this problem. Okay, so what is a superstring field theory? So by definition,
will also solve will also solve the previous.
Yeah, because once you have a string field theory, then you can use a momentum space. You never have to use the Schuringer parameter. You can do it if you like, right? If you want to use Schuringer parameter, you turn it towards I infinity, but you can just use momentum space integrals, right? And in the momentum space integral, of course, the previous problem was not there, right? Because k square plus m square is negative, that's perfectly fine as a propagator when we use momentum space representation. So once you have a string field theory, then all of these problems can be tackled at the same go, right? Because you have the standard field theory tools to address the amplitudes, to compute the amplitudes. Okay, so what is a string field theory? Okay, so by definition, it's a field theory whose Feynman rules What this means is that suppose you take this field theory, okay, and just write down all possible Feynman diagrams without ever worrying about LSZ or mass transformation or something. Okay, so you include Feynman diagrams like this, you include Feynman diagrams like this, okay, without worrying about the fact that the vacuum has to be shifted or the mass has to be renormalized. Okay. And then for each of these Feynman diagrams, you use Schuringer parameters, okay, integrate out the momentum. Then formally, it should look exactly like the string amplitudes that you have, that we can compute from the worldsheet perspective. Okay, that's the sense in which string field theory is equivalent to the standard worldsheet theory. Okay. But of course, once you have a field theory, okay, then you know that we shouldn't do what we are doing there. We shouldn't sum over diagrams of this kind, okay, or sum over diagrams of this kind. Whenever you encounter a diagram of this kind, you know that there is a mass renormalization going on here. Okay, so you have to use LSZ procedure and cut off the external propagator. Whenever you encounter a diagram like this, you know that the vacuum is being shifted. Okay, so you have to go to the shifted vacuum, expand around the new vacuum, and carry out your perturbation theory. Okay. So once you have a string field theory, you can carry out that procedure, and then you get a finite answer for all physical quantities. Okay, so that's basically the principle of using string field theory. Okay, that while formally it agrees with what the worldsheet theory gives, okay, it also has the intrinsic tools to remove the divergences that you normally encounter in worldsheet description.
After removing these particular contributions,
Yes.
can we try to go back?
Yes, you can try to go back, right? And this will correspond to making some corrections in the worldsheet description.
That would be something complicated in the world.
Well, it will be complicated. It will be a prescription of how to deal with regions near the boundary of the moduli space, right? It tells you that when you go near the boundary of the moduli space, and in string field theory, there is a very precise notion of from which point onwards you should modify your procedure, right? And from that point onwards, when you go near the boundary of the moduli space, it tells you that the integrand is not what it is. You normally see it as it is, but it has to be modified appropriately. Right? That's the way the prescription comes in when you try to convert the string field theory lessons to the worldsheet language.
For example, this problem of this beta function not vanishing.
Yes.
How is it affected by changing?
Yeah. So what will happen is that these diagrams in the language of string field theory, once you shift the vacuum, right, this will have to be accompanied by subtraction. The integrand will not be the integrand that will get directly from the worldsheet description, right, but it will correspond to removing the contribution from this massless sector. Okay. But at the same time, you have to add correction factors, right? Because the shifted field, once you have shifted the field, each of these vertices also get corrected, right? This, for example, will get now contribution from 4-point vertex with one leg coming out like this, right? So those corrections also have to be added. So string field theory will tell you exactly how each diagram has to be corrected, right? And with that, you recover the actual answer from string field theory.
Can I think of this as some kind of
Yes, you can, because going close to the boundary of the moduli space, right, is equivalent to cutting off the world sheet integral, right, at short distances. Okay, so indeed, so you are putting an ultraviolet cutoff on the world sheet theory, right, so that you never go, for example, they never let the vortex operators approach too close to each other. Okay, and when you are below that cutoff, it tells you that you have to integrate in a slightly different way, right, not in the standard way, because that will give a divergent answer, but you have to use certain subtractions and certain corrections, and then you integrate, right, and construction, those integrals will be all perfectly finite. Right, because in string field theory you wouldn't have these divergences, right? Here, for example, you will only allow massive states to propagate, but not massless states, right? Because the shift in the vacuum will cancel this diagram.
There's a space-time renormalization, what we are doing here by LSC or Massless.
Exactly.
And then there's a worldsheet theory renormalization. In the statement that these two are related.
Yeah, the point is infrared in space-time, right, is ultraviolet in the worldsheet. So putting an infrared cutoff on the space-time picture, right, which is cutting off the Schuringer parameter at a large value, right, is like putting on ultraviolet on a ultraviolet cutoff in the worldsheet picture. Right, that's the way these two are getting related.
Okay. So the renormalization about is there some precise statement about how the renormalization in the worldsheet?
Yes, the statement is in terms of the Schuringer parameter. That what we will see that in the string field theory, the Feynman diagrams, which has a propagator, right, comes from close to the boundary of the moduli space, right, and close to the boundary of the moduli space from the worldsheet perspective is ultraviolet, right, when 2 points are coming close to each other, right. So the contribution from the elementary vortices, okay, are giving the region in the bulk of the worldsheet, right, where you are not close to any boundary. Okay. And whenever you are close to a boundary, that in the language of the string field theory has one or more propagators built in, and the modification that you have to do, right, to get the finite answers in the Feynman diagrams which are propagators, right, like this one, right. If you didn't have any propagator, then there are no IR divergence of this kind, right, because k square plus m square is never 0. Right? It's only when you have propagators that you have IR divergence, and the diagrams with propagators are representing the worldsheet integral from near the boundary of the moduli space. Yes. 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 Yes, that's right. Yes, so here what I mean by cutoff on the worldsheet theory is when, for example, two vortex operators come close to each other. On the moduli space, exactly.
You remove the punctures.
Exactly.
Edges of the moduli space and put you there.
That's right. Yeah. Right. So this is like when you have two vortex operators coming close to each other. Okay. Or if you have switched on some background, right? Then it's like you are perturbing the worldsheet theory by some marginal operator, right? Or not marginal operator, in general, some operator. Okay. If it has a marginal operator, of course, it will be still a solution to the equations of motion. You are perturbing by some operator. Okay, but that is a divergent notion in the worldsheet theory, right? Because when the two operators come close to each other, then it's divergent. Okay? So you have to then say, when you talk about perturbing the worldsheet theory by some operator, that you have to have an intrinsic cutoff, okay? And that is again provided by the S parameter in the string field theory. Yes, it's the original worldsheet theory you assume is already renormalized, right? So you are not questioning whether the original worldsheet theory based on which you have formulated your string theory, string perturbation theory, whether that cutoff, that cutoff we don't even ever see, right? Because all the correlation functions are given irrespective of what that cutoff is. Right? Yeah, it's a CFT. Now the question is, in this CFT you can introduce vortex operators, right? And when the two vortex operators come close to each other, there is a possible divergence. That's the moduli space divergence that you're talking about. Or you can talk about perturbing this CFT by another operator, right? That's what will happen when there's a massless tadpole and you have to shift the background. Right? There you have to integrate over the whole worldsheet. You bring down the operator, many copies of the operator, right? And there is a genuine question of where to cut off this integral, right? Because when two operators collide, again there is a divergence. And that is automatically taken care of by string field theory. Right? So any extra cutoff dependence that comes in, okay, in doing this procedure is what string field theory provides. Right? It is not telling us about the original worldsheet theory, how it's defined with cutoff. Right? Because that you assume that there is a CFT anyway, and is defined in terms of correlation functions.
So this seems to say that the LSE, the space-time LSE,
Yes.
Gives you some natural, I don't know,
Natural to cut off the world sheet.
natural cutoff of the moduli space.
Or the moduli space, exactly.
Natural compact.
That's right. Well, it's not really a cutoff, because it's not that you are removing these Feynman diagrams altogether, right? You are just reorganizing them into something, right?
So if you correctly say it's a natural compactification?
Yeah, I think it's correct to say it's a natural compactification of the moduli space. It's telling you precisely how to compactify the moduli space.
And these are the kind of compactification that mathematicians.
Well, I think the kind of compactification that mathematicians talk about are not completely of this kind, because they don't talk about resumming. See, this, for example, the kind of compactification that you have here, right, it requires combining different genus contributions, right? I mean, when you try to do LS, you have to sum over all of these and, define a new propagator, right? That mathematicians never talk about. Compactify only individually genus by genus. Right? So this is going beyond what mathematicians normally talk about as compactification. Okay, because you really have to combine different genus contributions into one single entity.
You have to resum the moduli space of higher genus.
Exactly, that's right. But the point is, if you try to resum the moduli space of higher genus surface, that's a very complicated problem, right? What string field theory tells us is that you are not trying to resum everything, right?
Boundary.
Exactly, only near the boundary that you are resumming. Right? So string field theory, so that means the first thing you have to do is to have a natural notion of what is close to the boundary. Right? And that's what string theory provides by writing down a Feynman diagram decomposition.
In a way, all the moduli space of all genus surfaces is embedded in one, in a sort of a larger sort of universal
Moduli space, yeah. You can think of it that way, but the point is that's not what we are doing here, because in string field theory, of course, if you want to calculate the full amplitude, then you have to sum over all genera, right? But what we have here is that we are summing over the moduli space of different genera, but not over the full moduli space, right? You are only cutting off, identifying some region of the moduli space near the boundary, and that's what we are resumming, right?
So that's where you will be giving some uniform coordinates.
Exactly. Which will allow you to do that, and that. Exactly, and that's what string field theory does it naturally, right?
But you can then imagine that it is analytically. I mean, it's like you're gluing different genus moduli spaces near their boundary in some way, and then the whole thing gets sort of
that is true. Yeah,
glued up.
Yeah, exactly.
I mean, even usually mathematicians do think about different genus in the sense that sometimes
Yeah.
But this is not just splitting into two.
Yeah.
You're doing some
You're resumming, exactly. That's right.
summing this. Delhi moves to a compactification.
Yeah.
Quite give us the thinking one, right? Because that is really taking the boundary and replacing it with some, putting some good dimension one surface. That's not.
Yeah. See, the point is, we didn't use the Delin-Mumford compactification. The point is, if there is no mass renormalization, but only wave function renormalization, right, then the Delin-Mumford compactification by itself will be useful, because these diagrams will not be divergent, okay, but this will be finite. Right? If there is only wave function renormalization and not mass renormalization, there is a k square plus m square factor from here, which will cancel the 1 over k square plus m square. Right? So these will be finite diagrams, right? And then we don't have to carry out the full LSC. Okay, there is a way to then analyze these diagrams without using the full LSC procedure. Right? And their Delin-Mumford compactification is useful, because that's what you use to define these diagrams in that case. But once you have actual mass renormalization and you have to resum, right, then I don't think just Delin-Mumford compactification by itself is enough to handle the situation.
Some extension of Delin-Mumford compactification.
Well, I don't know how to put it mathematically. I know how to get numbers out of it, right? Yeah. But presumably there is a underlying mathematical description of this process.
People talk about this universal
Moduli space, yeah. Yeah. Yeah.
In Mumford compactification, I should think of it as just taking care of the wave function.
That's it. Yeah, that's what Witten did. That he used it to take care of the wave function normalization, right? Or when the these massless tadpoles vanish, right? When there are no massless tadpoles, right? Even then, there is some procedure you have to do to handle these diagrams, because this is again a finite contribution, right? But this is finite because there is a 0 times infinity. Right? This is 1 over k square, which is infinite. This is 0. Right? And again, you have to define it appropriately, and there again, Delaunay-Mumford compactification is useful in defining how to handle these diagrams. Right? So when the massless tadpoles vanish and the mass renormalization vanishes, then you can use Delaunay-Mumford compactification to give a well-defined procedure for what the string amplitudes are, computing what the string amplitudes are. Okay, I think I have about half an hour. It's about 4:30, I think, 4:20. Okay, so now I start with the real thing, okay, which is how to construct string field theory. So what I'll do today is to just give an introduction to superstring worldsheet theory. Okay, and next time I'll describe off-shell amplitudes and from there on to string field theory. Okay, so I'll assume that you're familiar with Polchinski. So what I'll do is to basically briefly review parts of Polchinski. Okay, but it will not be really an introduction to the basics. Okay, that I mean, if you have not seen it, perhaps you should read up Polchinski's chapter on the superconformal ghost system. Okay, so superstring worldsheet theory. Now, whatever I am going to describe is valid both for heterotic and type 2 string, okay, and possibly compactified. Okay, you don't have to assume that you are in 10 dimensions. But just for simplicity, I'll focus on heterotic string theory, okay, because the description is somewhat simpler there. Okay, just the notation is a little simpler, that's all. So this, first of all, has a mattered superconformal field theory. Okay. This has central charges CL/CR as 26 and 15. Okay, L for us will be the anti-holomorphic sector, R will be the holomorphic sector. This is the side on which there is a worldsheet supersymmetry. Then we have the ghosts. So ghosts have first BC. So these have CL/CR as 0 minus 26. Then you have B bar, C bar. These have minus 26, 0. And then finally beta gamma, these are the superconformal ghosts. These have 0, 11. Okay, so the total central charge is always add up to 0. Yeah, as you can see, 26 minus 26 is 0, and this adds up to 0. Now these are fermionic ghosts. These are bosonic. But to quantize superstrings properly, we have to bosonize. Bosonize in quotes, bosonize the beta gamma system. Okay. And so what we do is that we trade in beta and gamma in favor of 3 fields, 2 fermions and 1 boson, okay, with these relations. So here xi and eta are fermionic, and phi is a scalar with background charge. So we assign conserved quantum numbers. Oh, I should have said that the conformal weights, okay, BC of course we are probably familiar. This is 2, this is -1. Okay. This is 3/2, this is -12. Okay. And for xi eta, okay, this has conformal weight 0, 0. Okay, both left and right holomorphic right conformal weights are 0. This has left conformal weight 0, right conformal weight 1. Okay, so conserved quantum numbers are first we assign host number. This is taken to be B, B bar and beta has -1, C, C bar and gamma has +1. Okay. And in terms of xi eta, xi has -1, eta has 1, and e to the q phi has 0, okay, for any q. And we also assign something which is called picture number. So the picture number is e to the q phi has q, xi has 1, eta has -1. And this means that B, C, B bar, C bar, beta, gamma has 0 picture number. Okay, you can just add up and you can check that these all have 0 picture number, which basically means that the picture number arises only after this bosonization, right? In the original variables, there is no notion of picture number. Okay, but nevertheless, we will see that the picture number plays an important role because this bosonization is necessary for the quantization. Okay, now the conservation laws on genus G, need total host number 6 minus 6G and total picture number 2G minus 2. Okay, otherwise the correlation function vanishes. So if you have a genus G amplitude, okay, unless the operators that we insert in the correlation function has total host number 6 minus 6G and total picture number 2G minus 2, you will find that the result is 0. Okay. And I should also have said that total xi eta charge has to add up to 0. Okay, so total charge of xi, total number of xi's should be equal to total number of etas. Okay, are there any questions? Okay, now you can do a mode expansion. Okay, this is standard. I'll just write down a few. Pardon?
There is one more guy in the correlator to circumference.
Yeah, so I'm just coming to that. So this is in a small Hilbert space, but I'll introduce that in a few minutes. Okay, once we go to the small Hilbert space, then this is the conservation law, the equal number of xi's and etas. Okay, so the mode expansion, okay, B of z, for example, is sum over Bn z to the minus n minus 2, etc. Okay. But we'll be interested in xi and eta. So xi of z will have a mode expansion of the forms xi n z to the minus n, and eta of z will have sum over n eta n z to the power minus n minus 1. Okay, so these just reflect the fact that xi has dimension 0, this has dimension 1. And now we define what is called a small Hilbert space. This is a space of states annihilated by eta naught. Okay. And in terms of the vortex operator, it means the vortex operator depends on psi only through del psi. Okay. Some derivative of psi, it could be del square psi, etc. Okay, but no factor of psi. Because having a psi in the vortex operator means that in the language of state there is a psi 0 acting on the vacuum, and then eta 0 will not kill it. Okay. So we will be working always in the small Hilbert space. Okay, all our operators will be in the small Hilbert space, and this conservation law described here, that the total psi eta charge should add up to 0. Okay. That's for operators in the small Hilbert space. Okay, if you work in a large Hilbert space, then the total number of psi's is one more than the total number of etas, because you need an explicit psi 0 in the correlation function. Okay, so now some notation. So we'll define Tm and Tm bar as the matter stress tensor. T and T bar as total stress tensor, which means matter plus host. T beta gamma will be the beta gamma stress tensor. Tf will be the matter super stress tensor, okay, which basically means the fermionic component, fermionic super partner of the stress tensor. Okay, so this has dimension 0, 3 half, for example. So the BRST charge QB will be integral JB okay, I'll define what these are. So JB is C times Tm plus T beta gamma plus gamma Tf plus BC del C minus 1/4 gamma square B. JB bar is C bar Tm bar plus B bar C bar del bar C bar. And just based on the various operator product expansion, one can show that QB square is 0. Okay, so the BRST charge is important. Okay, are there any questions? Okay, now I'll introduce another very useful notion, picture changing operator. So this is defined as the anti-commutator between QB and Xi. Okay. And since I have explicitly given the expression for QB, you can evaluate it by looking at the operator product expansion of these with Xi, okay, and picking up the appropriate residue. And what one finds is that this is given by C del Xi plus e to the phi Tf minus 1/4 del eta e to the 2 phi b minus 1/4 del. Okay. So the first thing to notice is that this is BRST invariant. Second, it's in the small Hilbert space. Okay, because as you can see, it depends on Xi only through its derivative. Okay, there is an explicit factor of Xi, even though here it looked like there is an explicit factor of Xi. Okay. And third is that it's not trivial, not BRST trivial in the small Hilbert space. So BRST trivial means if it can be written as anti-commutator of QB with something. Okay. Now of course it is written as an anti-commutator of QB with Xi, but Xi is not in the small Hilbert space, right? So when you say that it's not BRST trivial in the small Hilbert space, means that it cannot be written as QB anti-commutator with something which is in the small Hilbert space. Okay. And the final property which gives its name is that it has picture number 1. Okay, essentially because QB has picture number 0 and Xi has picture number 1. Okay, and you can count each of these individually and you can see that they have picture number 1, each term. So this will play an important role for reasons that I'll explain soon. Finally, I'll give the normalization of the vacuum. So the vacuum will be characterized by the momentum that it carries. So it's like e to the I k dot x acting on the SL2R invariant, SL2C invariant vacuum. So C minus 1, C bar minus 1. Okay, so D is the number of non-compact dimensions. Okay. And notice that on genus 0, which is what this matrix element is about, genus 0, okay, we need total ghost number is 6 minus 6G, I had said, right? That is 6. That's what you have here, 4 factors of C, and total picture number was 2G minus 2, which is minus 2, and that's what you have here because of e to the minus 2 phi. Okay, so these are necessary in order to provide the correct host number and picture number. And this is the way we will normalize our vacuum. Okay. Now, given the matter and ghost superconformal field theory, we can of course build a whole Hilbert space of states in the matter times the ghost sector. Okay. But for our purpose, we will isolate a particular subspace of that Hilbert space, which will be important. Okay. So HT will be a subspace of matter ghost Hilbert space such that of GSO even states. Okay, I should have said that there is this GSO projection which removes half of the states of the theory. Okay, and I will assume throughout that I will be working with only the GSO even states, okay, which has already been projected, why the GSO odd states have been projected out already, okay, satisfying the following condition, that S belongs to HT if S B0 minus S is 0 and L0 minus S is 0. Okay, so what is B0 minus? So B0 plus minus will be defined as B0 plus minus B0 bar. And let me also add the definition, C0 plus minus is half C0 plus minus C0 bar. So LNs are the Virasoro generators. So let me write that down explicitly. T of Z, these are the total stress tensor, right? This has an expansion like ln z to the minus n minus 2. And similarly T bar of Z bar. Yes, so HT so far has all picture numbers. All picture numbers, right? We will be making a finer classification soon. Right now, HT only has these conditions, B0 minus and L0 minus and annihilates it. Why L0 minus? Well, it's a technical reason that, I mean, we will see that the off-shell amplitudes can be defined only for states with L0 minus equal to 0, right? And that I'll try to explain as I go along. And it seems that, I mean, you can impose a L0 minus equal to 0 constraint even at the off-shell level and still get a sensible string field theory. Yeah, you cannot define off-shell amplitudes without imposing this condition.
L0 minus equal to 0 is same as the level match?
Yes, it's the same as L0 level matching, exactly.
Only the level match states
are off-shell, exactly. So off-shell states all have level matched state. Yeah, they are all level matched. Okay, so this I can decompose into Nebuchadnezzar sector states and Ramon sector states. Okay, Nebuchadnezzar sector states have antiperiodic boundary condition, the Ramon sector states have periodic boundary condition. And these can be further decomposed as sum over Q belongs to Z HQ. Yes. No, no. So the off-shell states do not get annihilated by B0 or B0 bar, but they get annihilated by B0 minus B0 bar.
the usual string theory
The gauge fixed string field theory will have B0 plus also 0, right? But the gauge invariant string fields will relax that constraint, right? So B0 plus equal to 0 is a gauge condition. Right? That's why you are not putting it at the beginning. You can define off-shell amplitudes without imposing that condition. But defining off-shell amplitude with B0 minus equal to 0 condition relaxed, nobody has been able to do so far. Right? Eventually, for gauge fixed string field theory, you will also impose B0 plus on state equal to 0. Okay, but I am just keeping it general so that eventually you also want to go to gauge invariant string field theory, right, where you relax that constraint.
way that these two are sort of linked, the L0 minus and the B0?
Yes, they will be linked. Again, when we discuss the off-shell amplitudes, it will become clear why they are linked. Right? Yeah, basically the point is L0 minus equal to 0 condition allows you to identify the choice of coordinates up to phases. Right? And the B0 minus equal to 0 condition tells us that when you consider a tangent vector which rotates the phases, right, that tangent vector should act as a trivial tangent vector because we are identifying phase rotation. But this will become clear when we define the off-shell amplitudes, which will probably be next time.
S is killed by
Are the?
S killed by QB.
No, they are not killed by QB because that's the on-shell condition. That will come out as an on-shell condition. S is not killed by QB. So S, only these conditions, these are the only conditions that S satisfies. For open string field theory, there is no condition. You don't impose any condition at all. You work with the full off-shell Hilbert space. Okay, so these NS sector states decompose into these subspaces. So what is this HQ? This contains states of picture number Q. And these decompose into Q belongs to Z plus half HQ. Okay, so the NS sector states carry integer picture number, the Ramond sector states carry half integer plus half picture numbers. Okay. And now I'll define two subspaces which will play an important role. H hat T will be H minus 1 plus H minus half, and H tilde T will be H minus 1 plus okay, and basically we will see that the off-shell string fields will take value in H hat T. Okay, the interacting off-shell string fields will take value in H hat T, but this will also play an important role eventually. Okay. So these will be the subspaces that we'll be working on. Okay, H minus 1 you can see is common, right? So it's not that H hat T and H tilde T are mutually exclusive. Okay, the H minus 1 is common to both, but these are different. And you can also see that these Hilbert spaces are in some sense BPZ conjugate to each other, right? Because when you look at the inner product, this with this inner product is non-vanishing, right? Because total picture number adds up to minus 2. This inner product of this with itself is 0 because total picture number adds up to minus 1, right, which is not the right one. But the inner product between this and this is again non-zero because total picture number adds up to minus 2. Okay. So these two subspaces are conjugate to each other. Okay, so now let me explain the role of the picture changing operator and then I'll stop. Yes? Yes. So for type 2 theory, you will also have picture numbers on the left side, but these constants are identical. You don't have any further constant.
And here you put minus 1 comma minus 1.
Yes. So it will be minus 1 comma minus 1 and minus half comma minus half. Well, no, minus 1 comma minus 1 plus minus 1 comma minus half because you can have NSR states also, right? So all possible combinations. Okay. So this will be sum of 4 sectors. Okay. Minus 1, minus 1, minus 1, minus half, minus half, minus 1, and minus half, minus half, and here it will be minus 3 half. So you basically double the square it. I mean that's basically the philosophy. But there is no change here. These conditions are not supplemented by any further condition. Okay. Now it turns out that each physical NS or R sector states, each physical NS sector states as a representative in HQ for every q which is integer. Okay, and if you replace it by R, then this will be q belongs to z plus R. Okay, so the physical states don't belong to a given picture number. They in principle belong to all picture numbers which differ by integers. Okay. And this makes things inconvenient, okay, because for example, if you allow an off-shell string field to be an arbitrary element of HNS, right, then an off-shell string field will contain one representative in each picture number, right? So there will be infinite number of physical states for one particular NS sector state, right? There will be infinite number of gravitons, for example, okay, which is what you don't want, okay, and that's why you want to restrict to a given picture number.
All these vectors can take
by picture number, yeah. So let me, that's what I was going to write. So if you take Vz comes to HQ, okay, and then the way you construct the corresponding state in HQ plus 1 is by taking the product of the picture changing operator with V of Z. Okay, and this, and you have to remove the singular piece, but after that you, whatever you get that's the state in HQ plus 1. So picture changing operator basically take you from one sector to another sector. Yeah, all in small Hilbert space. So I mean, I'll be working throughout in small Hilbert space. I'll never talk about large Hilbert space unless I specifically mention, right? Maybe once or twice I may mention, but otherwise all our operators will be in the small Hilbert space. Okay, any other question? Okay. So because of this ambiguity, we'll have to choose specific picture number. So we'll take general off-shell string state to be in h minus 1 plus h minus half, which is precisely h hat. What did I call it? H hat t. Well, for on-shell you can in principle, right? Even though that has some subtleties, right? For off-shell you cannot, because what happens is that if you take any picture number other than -1, for example here, you get states, off-shell states whose conformal weight is unbounded from below, right? And which means that if you try to construct a string field theory based on those which are propagating in the loops, right, you will get contribution from states which have arbitrary negative mass square, right, which is what you want to avoid. So basically this is the unique choice, right? For Ramon sector one could have done with h minus 3 half, okay, because h minus half and h minus 3 half are the two sectors which has spectrum bounded from below, but this seems to be the more natural choice, okay, although the other one will play some role, as we will see. Subtleties for on-shell. Basically, if you use states in other picture number, you don't get the correct boundary terms. I mean, you may miss some of the boundary terms, total derivative terms, okay, and which can get non-zero contribution to the boundary, right, and give you wrong answer. So if you start from the supermoduli space, then this is the result that you arrive at naturally. Okay, if you use the Deligne-Mumford compactification of the supermoduli space, then you see the factorization always occurs on these in this Hilbert space. Super Riemann surface, exactly. That is for the supermoduli space. Okay, so now if we consider a general, suppose we take a genus G amplitude with m ns and n Ramon sector states. okay, and we will be taking the states in this Hilbert space, okay, which means that the total picture number that we have is minus m minus n by 2. Okay. But we need 2g minus 2. This is what I had said, that if you, unless you have 2g minus 2 picture numbers, total picture number 2g minus 2, the result vanishes, right? So that means you are missing a picture number of 2g minus 2 plus m plus n by 2. Okay. And these have to be supplied by explicitly inserting the picture changing operators in the correlation function. Okay. So we supply 2g minus 2 plus m plus n by 2 PCOs in the correlation function. Okay, I'll write down later the explicit expression for the correlation function that we need to evaluate. Okay, but this basically shows why we need picture changing operators, why the picture changing operators are important, because in order to define an amplitude on a genus G Riemann surface, okay, we have to compensate for the fact that the total picture number here adds up to minus n minus n by 2. Okay, but what we need is this, okay, and hence we have to add these many picture changing operators. Okay. Now you may ask, where should we insert them? Okay. For on-shell amplitudes, one can formally show that it doesn't matter where you insert them, okay, except that there can be boundary terms, okay, which we have to be careful about. Okay, and that's why again string field theory comes into play. We will see that in string field theory there is absolutely no ambiguity. Okay, it tells you exactly how to handle this. There is still ambiguity in defining off-shell amplitudes, but those are irrelevant when you actually go to on-shell S matrix elements. So I think I have more or less given the background. So next time we will use this data and start defining off-shell amplitudes in string field theory. Okay, so let me maybe just say one word about the philosophy of constructing string field theory. See, normally in a field theory you first write down an action, then you gauge fix, then you derive the Feynman rules and compute S matrix element, right? Here the way we will proceed is exactly in the opposite direction, because you already have an expression for the formal expression for the S matrix elements from the worldsheet theory. Okay? So our goal here is to reproduce those S matrix elements first, right, at a naive level. Okay? So we'll first generalize the on-shell amplitudes into an off-shell amplitude. Okay? Then we'll try to write down a gauge fixed action which gives those off-shell amplitudes. Then we'll see where that gauge fixed action comes from a gauge fixing of a gauge invariant action. Okay? And then eventually we'll write down the action. Okay? So it will be exactly in the opposite direction, because you already have knowledge about what you want to reproduce, right? Which is not the case in quantum field theory, right? There we start with an action and compute the S matrix element. So that's the reason why next time we'll start writing down the off-shell amplitude, and then we'll go backwards from there and try to construct the action that gives rise to the off-shell amplitudes. Okay, so I think I'll stop here. That's right.
So, but that doesn't take care of this mass normalization.
No.
So, but from mass normalization, if it is generalized, we don't get any additional.
Well, that, I mean, I don't know how to directly convert to this language, right? So this automatically fixes what the off-shell string field should be, right? There is no further freedom. Then the mass transformation gives you how to handle that, right? There are additional divergences that you find if you use naive string perturbation theory, and the mass transformation procedure tells you how to handle those divergences.
It's really just the factorization part of it.
Exactly. So the point is that by choosing this, what we are ensuring is that when you factorize, when an amplitude factorizes, what propagates in the tube, okay, are states in this Hilbert space.
So mass renormalization does not change what you expect.
That's right, exactly. I mean, if it changed, it would be very strange, right? Because then, I mean, after all, there is only one string field theory. In some cases, there may be mass renormalization, in some cases, there may not be, right? So you don't want to have to change the prescription when there is mass renormalization. Right? So the mass renormalization doesn't require us to change this procedure. Right? Mass renormalization says that once you have a string field theory, then you apply the usual field theoretic rules to renormalize your mass.
definition of HT.
Yes.
Is the reason we impose this, for example, if we do world line theory,
Yes.
we would not get these, we would get an L0 constraint. It's not an.
No, in the world line theory, the off-shell states don't have the L0 constant, right? Because L0 constant will be like k square plus m square equal to 0. That comes as a part of the equation of motion, right? So here, these constants are being satisfied by off-shell states.
Yes. So there's no level matching in the world line theory.
Exactly, there is no notion of level, exactly. Neither is it there in open string theory, for example, right? Open string theory has no constants of this kind.
So is the reason we impose this is to bring it close to open string or the world line theory?
No, not just that, right? It's, I mean, when you define the off-shell amplitudes, perhaps it will become clearer that off-shell amplitudes require that you should be able to define something called local coordinates. Okay, that each vertex of order has to be inserted with some local coordinates, because once it is off-shell, then the result depends on a choice of metric, right? And if you change the phase of the local coordinates, okay, if you don't impose this condition, okay, the result for the amplitude will also depend not only on the local coordinate fully, including the phase. Okay. But what one can show that there is an abstraction to choosing local coordinates globally, okay, keeping the phase information. That you may choose some phase information around the local coordinates, but by the time you have gone around a closed cycle in the moduli space, that phase gets rotated. Okay. So you cannot define off-shell amplitudes if the off-shell amplitude is dependent on the phase of the local coordinate. Okay.
So in some sense we have already summed over the phases, integrated over the phases.
Yes, in some sense you have integrated over the phases.
That's what imposes.
Exactly. That's what imposes this condition, right? So in the language of string field theory, we will see that this comes because you have already integrated over the phases. When you try to convert the string field theory amplitude to the standard moduli space integral, right, we will see that the way it comes is that the phase the L0 minus is represented as a phase integral, and that becomes part of the moduli of the theory.
That is for the external state.
No, even for the internal states.
The internal states, there, of course, once you integrate over the moduli, then you do the
yeah. So the point is the internal. Take for example the genus 1 moduli space, right? So on this part, you have the full tau1 integral, which is the analog of the theta integral. Okay. So the propagating states. So the point is this part of the moduli space is represented by Feynman diagrams with the propagator. Okay. Take say a 1-point function of the genus 1 surface. So this is the propagator. Right? What is propagating here are the ones which are satisfy L0 minus equal to 0 condition. Okay? And this diagram covers this part of the moduli space. Okay? The integral over this part will be covered by an explicit vortex. Okay, where you don't think of this as anything propagating, this is part of the definition of the string vortex. Okay, 1-point vortex of the string. It's something that is explicitly there in the action. So all Feynman diagrams, okay, will only represent part of the moduli space where the structure is like this. Okay, this part of the moduli space where you don't directly see the L0 equal to L0 bar projection, in the language of string field theory, that's covered by part of the vortex. Okay, so the full genus 1-point function will contain a contribution from this diagram and a contribution from this, because there will be an explicit linear term added to the action, which will give this contribution. And the sum of these two will reproduce the full world state integral. For on shell, of course, you could try to represent the whole thing as a Feynman diagram without imposing this constraint. But as I said, once you relax this constraint, then the off-shell amplitudes are ill-defined. Oh no, that's just a convention. I mean, with this half, the commutation relation between C0 minus and B0 minus is just 1, right? Otherwise, you'll have a 2. That's all. I mean, it's just normalization convention. I mean, I could have put 1 over root 2, 1 over root 2, for example, to make it more symmetric, but this is equally good.